Hello everyone. In today's lecture, we will see a theory portion of maxima and minima. The images used in our slide deck are for educational purposes only. We respect the intellectual property rights of the original creators and owners of these images. If you are the owner of any of the images used in this deck and have any concerns or issues, please contact us at sathee@iitk.ac.in and we shall remove the images. Let's see first which topics we will cover in this lecture. First, we will see what is maxima and minima of a function. After that, we will see what is critical point. We will see methods to find local maxima or local minima. Second, or higher order derivative test. After that, we will go to the point of inflection, nth order derivative test, concept of global maxima or minima, some important results on maxima and minima, right? Okay, so let's start. First thing is maxima and minima of a function. A function fx is said to attain a maximum at x equal to a if there exists a neighborhood of a minus delta to a plus delta when x not equal to a, that is fx less than fa for all x belongs to a minus delta to a plus delta. When x not equal to a into h greater than 0, very small quantity, right? Delta is very small quantity. In such case, fa is said to be maximum value of fx at x equal to a, right? A function fx is said to attain a minimum at x equal to a, if there exists a neighborhood of a minus delta to a plus delta such that fx greater than fa for all x belongs to a minus delta to a plus delta when x not equal to a, right? Here you can see the graph of a function c. We have a graph of a function in which, see, this is local maximum, right? This is this is again local maximum. This is local minima, right? This thing here is greatest value, that is absolute maximum, right? Absolute maximum, or it is also called global maximum. This is least value, that is absolute minimum, or also called global minimum, right? Graph of a continuous function explained local maxima or minima and absolute maxima minima. In such a case, fa is said to be minimum value of f if at x equal to a, right? The points at which a function attains either the maximum or minimum values are known as extreme points, right? Or turning points. See, these points are basically either extreme points or turning points, clear? And both minimum and maximum of fx are called extreme values. The turning points A and C are called local maximum, and points B and D are called local minimum. Right? The turning points A and C are called local maximum, and points B and D are called local minimum. Okay? Got it? Now, let's discuss what is critical point. A point C in the domain of a function f at which either f dash equal to 0 or f is not differentiable, right? Two conditions should be satisfied. First is f dash equal to 0 at any point C, and second condition is f is not differentiable, is called a critical point of f. We can note that if f is continuous at point C and f dash C is equal to 0, then there exists h greater than 0 such that f is differentiable in the interval c minus h to c plus h, right? F is differentiable in the interval c minus h to c plus h. Now the converse of above theorem need not to be true. The converse of above theorem need not to be true. That is a point at which the derivative vanishes need not to be a point of local maxima or local minimum, right? Clear? So this is basically the discussion of critical point. Okay. Let's move to the method to find the local maxima or local minimum. See, first is first derivative test. Let's move. Let f be a function defined on an open interval I and f be continuous at a critical point c in I. Then, if f dash x changes sign from positive to negative as x increases through c, that is, if f dash x greater than 0 at every point suddenly close to and to the left of c, and f dash x less than 0 at every point sufficiently close to and to the right of c, then c is basically a point of local maxima. Okay, you have to remember this. Next, if f dash x changes sign from negative to positive as x increases through point c, that is, if f dash x less than 0 at every point sufficiently close and to the left of c, and f dash x greater than 0 at every point sufficient close and right of c, then c is a point of local minimum. Third, if f dash x does not change sign as x increases through c, then c is neither a point of local maxima nor a point of local minimum. In fact, such a point is called point of inflection, right? In fact, such a point is called point of inflection. Next one. See, from the figure, you can see that. See, here, this point, suppose this point, the left of this point here, x is greater than 0, right? And at this point where f dash c1 is equal to 0, left of this point is f dash fx greater than 0, and right of this point is basically fx less than 0, right? So, that is, left of this point is basically f dash x greater than 0, and right of this point is basically f dash x less than 0, right? So, at this point, at this critical point, f dash x is basically changing from positive to negative, right? So this is the point of local. This is the point of local maxima. Clear? Similarly, this point, the f dash x changes from minus f dash x changes from negative to positive. Then this point is local maxima, right? So by this way, point is local minima. This point is local maxima, right? Clear? This point is the point of non-differentiability and point at local maxima. This point is point of non-differentiability, but it is a point of local minima, right? So you can remember this. Now, graph of f around C explained following points. C, as we have discussed, if C is a point of local maxima of f, then fc is local maxima of f, right? Similarly, if C is a point of if C is a point of local minima of f, then fc is local minimum of f, right? You have to remember this, right? Okay. This was the first derivative test to find local maxima or local minima. Next part is find f dash x. See, the method is first find f dash x and equate it to 0. Right? Solve f dash x equal to 0. Let its root be x equal to a1, a2 till an. Right? Now find f double dash x and at f double dash x and at x equal to a1. If f double dash a1 is positive, if f double dash a1 is positive, then fx is minimum at x equal to a1. And if f double dash a1 is negative, then fx is maximum at x equal to a1. Third, point A, if at x equal to a, f double dash a1, if at x equal to a1, f double dash a1 is equal to 0, then find f triple dash x, find f triple dash x. If f triple dash a1 not equal to 0, then fx is neither maximum nor minimum at x equal to a, right? If f triple dash a1 is equal to 0, then find f4 times x, then find f4 times x. If f4 times x is positive, minimum value, then and f4 times x is negative, maximum value. If at x equal to if at x equal to a1, f4 times a1 is equal to 0, then f5 times x and proceed similarly, right? So you have to follow this pattern to find whether it is maxima or minimum. Clear? So this is second or higher order derivative test. The last thing that we have discussed was first order derivative test. This one is the second or higher order derivative test. Okay, got it? Next point is point of inflection. What is point of inflection? So at point of inflection, it is not necessary that first derivative is zero, right? At point of inflection, it is not necessary that first order derivative is zero. Second derivative must be zero. At point of inflection, second derivative must be zero, or second derivative changes sign in the neighborhood of point of inflection, right? Two things. It is for point of inflection. Two things are there. First, it is not necessary that its first order derivative is zero, right? And second derivative must be zero, or second derivative changes sign in the neighborhood of the point of inflection, right? You have to remember this. Okay. Next one is another derivative test. Let f be a differentiable function on an interval I, and a be an interior point of I, such that f dash a is equal to f double dash a is equal to f triple dash a till f n minus 1 a is equal to 0, and f n a exists and non-zero and is non-zero. Then important results. If n is even and fn a less than 0, this implies x equal to a is a point of local maxima, right? If n is even and fn a greater than 0, this implies x equal to a is point of local minimum, right? Next point if n is odd, this implies x equal to a is a point of neither local maximum nor a point of local minimum. Now the function f(x) equal to ax plus b upon cx plus d has no local maximum or minimum regardless of values of a, b, c, and d. The function f theta is equal to sine to the power m theta into cos to the power n theta attains maximum value at theta is equal to tan inverse root over m by n. If AB is diameter of circle and C is point on the circumference, then area of triangle ABC will be maximum if triangle is an isosceles triangle, right? You have to remember this thing, right? This can be asked in a fill in the blanks type question, right? Or also in a statement type question, right? You have to remember this. Next thing is concept of global maxima or minima. Let y equal to fx be a given function with domain D and a to b belongs to a to b is subset of domain D. Then global maximum or minimum of fx in a to b is basically the greatest or least value of fx in a to b. And global maximum or minimum in a to b would always occur at critical points of fx within a to b or at endpoints of the interval, right? Now next, global maximum or minimum in a to b. In order to find the global maximum or minimum of fx in a to b, step 1, find out all critical points of fx in a to b, that is all points at which f dash x equal to 0, and let these points are c1, c2 till cm. Step 2, find the values of fc1, fc2 till fcn, and also at the endpoints of domain, that is fa and fb. Step 3, find m1 global maxima or greatest value, and m2 global minima or least value, where m1 is equal to maximum of fa, fc1, fc2 till fcn and fb, and m2 is equal to minimum of fa, fc1, fc2 till fcn and fb. Clear? You have to remember this. Got it? Now, some important points and results on maxima and minima. Maxima and minima occur alternatively, that is, between two maxima there is one minima and vice versa. Next one is if fx tending to infinity as extending to a or b and f dash x equal to 0, only one value of x, that is say c, between a and b, then fc is necessarily the minimum and least value. Next point is if fx tending to minus infinity as x tending to a or b, then fc is necessarily the maximum and greatest value. Next, point 4, the stationary points are the points of the domain where f dash x equal to 0. Right, the stationary points are the points of the domain where f dash x equal to 0. Clear? You have to remember this. Next is summary of this chapter. What we have studied till now. Let's discuss. We have studied maxima and minima of a function, in which we have studied a function fx is said to attain a maximum state to attain maximum at x equal to a if there exists a neighborhood a minus delta to a plus delta x not equal to a, that is fx equal to 0, a very small quantity, right? Now we have discussed critical points. A point C in the domain of the function f at which either f dash 0 is equal to 0 or f is not a differentiable. F is not differentiable is called a critical point of f, right? Next, we have discussed different methods to find local maxima or local minima. In which we have seen first derivative test. We have seen second order or higher order derivative test. After that, we have seen what is point of inflection, right? And we have seen nth derivative test. After that, we have seen concept of global maximum or minimum, in which we have seen let y is equal to fx be a given function with domain D and a to b is subset of D, then global maximum or minimum of fx in a to b is basically the greatest or least value of fx in a to b. After that, in the last, we have seen some important results on maxima and minima, right? Hope you understood the concept behind the maxima and minima, right? The main thing in the maxima and minima is that we first find f dash x, and after that we will put f dash x equal to 0. And after that, we applied different tests, that is first order derivative test, second order derivative test, till nth order derivative test, like that, to obtain whether the critical points we have obtained is either maxima or minima, or and also you have to remember that you must take the end points also, right? Clear? Because uh, sometimes in place of critical points, end points becomes maxima or minima, right? So you must have to check end points also, right? So in this way, we have seen the basic structures of maxima and minima. In next chapters, in the upcoming lectures, we will see different types of questions that can be asked in our examination based on maxima and minima, and we will do different types of basics and some advanced questions also. Okay. Okay. Hope you liked the lecture. You understood whole concepts. Okay. Thank you so much.